Hopefully nothing happens. Okay, so we are going to be working on chapter 14 today. So my goal is to get this whole chapter done today in one go. Okay, since some of you have worked on the homework, hopefully you've noticed a change in chapter 14. And with chapter 14, essentially, as far as this book is concerned, chapter 13 was the last part, the last chapter in the intro to organic section. So we are done with organic, right? So don't celebrate yet. We're now moving on into biochem. So this part is an intro, sample chem class is really like. You happen to major in chemistry or minor, you be taking the of each of the, 1405 does the intro to G, and then 1407 does the intro to organic and then biochem. So the neat thing about the biochem part is we see chemistry in action in biology. Okay, so we're going to start. Our reactions will be somewhat familiar because we've seen them in a simpler version when we're dealing with the organic part, but we'll see them now in biomolecules. So we're starting with carbohydrates. And as far as carbohydrates are concerned, these are called sugars and starches, and they're polyhydroxy aldehydes or ketones. So remember the aldehyde or ketone family or group? We're now seeing aldehydes and ketones in the context of carbohydrates. And we're told that these aldehydes and ketones are essentially sugars, but their general name is carbohydrates or carbs. They are polyhydroxy, meaning that within each sugar molecule, you have many hydroxy or hydroxide groups. So we have many alcohol groups, and we have at least one aldehyde and one ketone. And so as we're looking at these, we'll see these as compounds that can be hydrolyzed to them. So we'll be looking at different sugars, simple sugars, and then more complex sugars as we deal with starch and cellulose and things like that. Carbohydrates can be classified into monosaccharides, disaccharides, and polysaccharides. So we're dealing with the simple versions, right? With monosaccharides, we'll see one molecule of sugar. With disaccharides, we'll see two combined together. Polysaccharides, we'll see many units of the sugar molecule. When we're dealing with carbohydrates, these are synthesized in green plants through photosynthesis, a process that uses energy from the sun to convert carbon dioxide and water into glucose and oxygen. We know that plants are usually planted, no pun intended there, to use up the carbon dioxide from the atmosphere. As we are living things, humans, animals, we breathe oxygen in and take out and expel carbon dioxide. A lot of the industrial processes that we do release a lot of carbon dioxide. Since plants take in carbon dioxide, we tend to plant a lot of plants, right? We plant a lot of plants to use up the carbon dioxide. In that process, they do make glucose. So in the body, glucose or carbohydrates in general are used for a burst of energy. If you're working out, they should tell you load up on carbs before you work out. And remember, the form of carbs that we need for immediate source of energy is glucose. Now remember, when we talk about proteins and then the fats and other macromolecules, we tend to focus on glucose as having the immediate energy, right? Immediate burst of energy. If you look at the Krebs cycle, if you had biology, the glucose molecule can easily get into the Krebs cycle. For the fats and the proteins, these have to be processed before they can join the Krebs cycle to harness or gather energy, okay? Okay, so here we're seeing how plants are actually storing energy in glucose, right? So here, this is happening in a plant. So my biology is not that great, even though I did double major in biology. It's a little, for me, it's a little bit harder to recall than chemistry. Chemistry is a lot easier, just for me, because I spent more time in chemistry than I have in biology. But this is happening in a plant. The plant takes atmospheric CO2, carbon dioxide, and uses water too, that we use when we water the plant, to convert both of these into glucose. So each of these cycles of the reaction produces one glucose molecule. We eat plants, we eat animals, and through that process we get glucose and other nutrients. You see right here, as the plant uses up carbon dioxide, it also releases oxygen, which is good for us. It filters the air by getting rid of CO2 and adding oxygen. Okay. So moving on to the chemistry. Once this glucose is made, now what? We're going to classify the different kinds of sugars, starting with monosaccharides. Monosaccharides are the simplest carbohydrates, and I'm using the term sugar. Remember, sugar slash carbohydrates, it's kind of, sugar is a common word for carbohydrates. So we're starting with the simplest form, which is monosaccharides. Monosaccharides will have between 3 to 6 carbons in each chain. And remember, they have to have either aldehyde or ketone group. So we have that carbonyl group, right? We talked about either aldehyde or ketone. And of course, each sugar molecule has a lot of alcohol groups in it. We talked about a sugar alcohol like xylitol and things like that. Sugar molecules tend to have a lot of alcohol groups in them. But while the groups are present and there are many, they're not dominant enough for the sugar to be classified as an alcohol. Okay, so we have so many competing functional groups in there, and so what we get is kind of a mix of all of them. Okay, so we're told here in the monosaccharides, you can have 3 to 6 carbons in your longest chain, the central chain. As you can see here, the carbons are lined vertically. By the way, in this section here, the carbons are lined vertically versus horizontally, something that we saw in the organic portion of this class. My goodness, I can't speak today. Okay, if you have a sugar with an aldehyde group, the common term is aldose sugar. So please notice the suffix here, OSE, stands for sugar. And if you've had a biology class, ASE is usually used for enzymes. So OSE is for different kinds of sugars or carbohydrates. ASE is for enzymes. So we have an aldose sugar, a ketose sugar, and you want to be able to identify one from the other. For the aldose sugar, you're looking for the aldehyde group. Remember, that's this group right here. The carbonyl with the hydrogen on one end and the rest of the chain on the other end. Or you're looking for a ketone, right? In the ketone, your carbonyl carbon will not be terminal. There'll be at least one carbon on either side of the ketone group. And that will be the ketose sugar in this context. Once again, notice that the central atoms are listed vertically this time versus horizontally. We'll get to a point where we list it horizontally, but that's when we're trying to get the cyclical form or the cyclic form of the sugar. So here we're told that monosaccharides with a carbonyl carbon at carbon 1 are called aldoses. Remember, in the aldehyde, so say here, in the aldehyde, we saw this before, the carbonyl is terminal. Terminal means on the end. There's nothing wrong with it. It's not sick. It just means on the end, right? Terminal. So it shows you right here, the carbonyl at carbon 1, that will be right here, will be terminal. So you see the carbonyl on the carbon 1 position. If the carbonyl is in carbon 2 position, this would be a ketose sugar. So right here, this would be an aldose. If the carbonyl is on carbon 2 right here, this would be a ketose. Okay, so either aldose on carbon 1 or ketose on carbon 2. You can't have both in one structure, so you either have the aldose or the ketose. Okay, so this is kind of unfolding the structure as we get into it. So I've mentioned this right here. I can move on. Okay, the simplest aldose is called glyceraldehyde. Okay, so notice the term here, aldehyde. And glycer, that's just a prefix, but glyceraldehyde, that's a common name. So we don't really have systematic IUPAC names here. This area is kind of a different group of chemists. you can sense the difference in the way they name things. They are somewhat specific, but not as specific as the IUPAC system we had with the organic group. So biochemists in real life are very different from organic chemists as a group of people, okay? So here we have more common names versus systematic names. Aldehyde, glyceraldehyde. The simplest ketose sugar is dihydroxyacetone. And you can tell once again from this part of the name, this has an aldehyde in it, and you have acetone, O-N-E goes with ketone groups, okay? So we're told these two are related. How do we know that? They're constitutional isomers of each other. That means they have the same general formula, C3H8O3, but these are arranged differently. Now, if you look at this right here, let me try to add a page. Okay. If you look at this right here, remember the CHO group? The CHO group is essentially the aldehyde group. So I'm going to draw this out so you can see. We have this right here. And this is carbon 1 essentially, right? So carbon 1 is your terminal carbon. That means this is an aldose sugar. And we have a total of 3 carbons, right? And in the middle here, you have a hydroxide group on the right, a hydrogen on the left, and on the far end, or I guess the bottom, you can say a hydrogen here, a hydroxide here, doesn't really matter. They'll tell you later on how to know where the hydroxide is based on the L or D designation. We're not there yet. So for right now, I just write it right here, and then you have the H. Okay, this is the aldose. And the term for this is glyceraldehyde. On the right side, we once again have 3 carbons here. On the top, we have, let's see, I put the H on one end, or the OH on one end. Doesn't really specify which side. Once again, the group of chemists that came up with this part here, this information, are very different from the others. So they're less specific, okay? So we have dihydroxyacetone. I'm not done with this structure. I have a OH. Oh, sorry, carbonyl right here. And here I have glyceraldehyde. Okay? And if you count the number of carbons, you should have 3. Number of hydrogens should be 8. Number of oxygen should be 3. Okay? The biggest thing here I would say is knowing how to draw them, knowing what name goes with which structure, and being able to input this in your homework, right? That's the biggest challenge here. These do have a general term to refer to either the aldose sugar or the ketose sugar. The monosaccharides are characterized by the number of carbon atoms in the longest chain. If you call a sugar a triose, that means that that sugar has 3 carbons in it. Now they'll use the term triose and then tell you like maybe a triose that's an aldehyde or triose that's a ketone, right? They have to be a little bit more specific there. So you have a triose, meaning has 3 carbons. A tetrose has 4 carbons. Please notice this time for this group of people, the prefix used to describe 4 carbons is not bute. So we don't use bute here. Even though the group of organic scientists, we use bute to refer to 4 carbons. With this group of people, we're now back to TETR, like tetrose, tetra, okay? So tetrose refers to 4 carbons. We have pentose, they all agree on the prefix here, pentose 5 carbons, hexose 6 carbons, okay? So in terms of these combined words we just learned, glyceraldehyde, since it has 3 carbons, will be aldotriose. Aldo telling you it's an aldehyde sugar, and then triose telling you that it has 3 carbons, okay? So aldo, we have the aldehyde functional group, okay? 3 carbons in longest chain. And then O's is the sugar or a carbohydrate. I guess that's a more technical term. Carbohydrate, if I can spell correctly. Okay, same thing over here. Ketone, we have ketone, as a functional group. Remember what that means, right? Aldehyde up here means your carbonyl is the first carbon. I forgot to write that here. With the ketone, your carbonyl is the second carbon from the top. That's important, right? We'll see later on. It's always second from the top because they write this out vertically. And then tri means we have 3 carbon. O's means we're dealing with a carbohydrate. Okay. So once we've seen all that, we're going to go through this here. Classify each monosaccharide by the type of carbonyl group and the number of carbons in the chain. Okay, so remember here we wrote the aldo first, number of carbons in the O's, right? So I'll go here. Of course, remember the CHO is an abbreviation for carbonyl and then hydrogen. So carbonyl is in the first carbon, so we know it's an aldehyde, right? This is going to be an ald that they have up here, aldo. Okay, how many carbons do we have? We have 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So this is going to be pent, right? And then we're dealing with a sugar, aldopentose. So once again, systematic, but not as technical as the IUPAC system we're using for organic chemistry. Okay, we're now moving on to this part here. You can clearly see that the carbonyl carbon is the second one, right? So we're going to say here, keto, to be consistent with what we have up here, right? Next number of carbons, 1, 2, 3, 4, 5, 6. Hex. Okay, ketohexose. Keto because we have a ketone sugar, the carbonyl is the second carbon, and then yeah. So you want to be aware, you want to know how to classify your sugar molecule, your carbohydrate molecule based on this system. Okay, once again, this is not necessarily a IUPAC system. Okay, here, let's see. Oh, remember these do have their own names. This is the ribose sugar. This is the fructose sugar. This is a sugar. In the fructose sugar, this is a sugar we usually have in different fruits and sweets and stuff like that. Well, mostly fruits. Okay. So here we're told to classify each monosaccharide by the type of carbonyl group and the number of carbons in the chain. Oh, this is a continuation. Okay. I'm trying to make sure it's not the same as the other one. Okay. Neat. So we have, let's see, aldehyde again, CHO. So aldo, 1, 2, 3, 4, 5, pent, O's. Okay. Here, once again, I'll go a little faster since we've gone through this before. Keto, 1, 2, 3, 4, tetrose. I was about to say butose. I'm like, no, this is the wrong section. Keto tetrose, right? Because tetra, like we did with tetrahedral before, yeah, they go with that prefix. Okay. These sugars they have here, I don't think it's anything that you guys can necessarily relate to, so I'm just going to keep going. Okay, here, they want us to draw a structure of an aldotetrose. So with this part, since it's just a generic formula, it doesn't necessarily have to match any of these that we have seen here. The most important thing is that we have our aldehyde group if it's an aldehyde, or a ketone group if it's in a ketone. And for our ketone, it's important for us to have the CH2OH on the top and on the bottom. On the aldehyde, I didn't mention that we only have one CH2O. Okay, so I need to make sure I mention that, which is important when we're drawing this out. In the aldehyde, on one end you have the carbonyl carbon. That's the first carbon. On the far end, on the bottom, you have CH2OH. So this has essentially been condensed. In the ketone or the ketose sugar, since the ketone group or the carbonyl group is the second one, we have this condensed form on both ends. Okay? CH2OH. So we're told here Draw the structure of an aldotetrose. Okay, I'll start with the first one. Aldotetrose. Okay, so I know it's an aldehyde sugar, so I'll start by, I'm actually going to draw this part out like that. Okay, this is my first carbon right here. It says tetra, that means I need 3 more carbons to make 4, right? So 1, 2, 3. Oh, I almost ran out of room right there. So this is 2, this is 3, this is 4. 4 total. Yeah, 4 total. Okay. So I know on the far end, on the bottom of the molecule for any kind of aldose sugar, I'm going to have CH2OH. And this is usually written in the condensed form. Yeah, CH2OH. I want to remove the C4 from here because it makes it look weird. So CH2OH. Now for the middle part, since this is generic, you can put your OHs wherever you like. We know on one side there is an OH, on the other side there's an H. This is not necessarily tying into an actual molecule. So I can put my OHs on the same side if I want. I can flip them over, but usually one side has an OH, the other side has an H. So you could do it like this, or you could flip it and do it this way. All they want to make sure is, they want to make sure when you're drawing your structure out, you're following the principles, okay? For ketopentose, I have to start a little higher. For my ketopentose, I need a space. So I'm going to start with my first one being like this, CH2OH. Then the next one is my carbonyl carbon. So this is going to be carbon 1, carbon 2, right? Then carbon 3 will be here, carbon 4, carbon 5. I have to have the ketone group. The carbonyl has to be the second carbon. I need to have 5 carbons, and the whole structure is a sugar. So 1, 2, 3, 4, 5. I know I have 2 of these groups, top and bottom. Once again, for carbon 3 and 4, I get to quote unquote freestyle, right? I can put my OHs. Let me try to mix this up a little bit. Put this right here, or I can do this like that. It's really up to me because I'm not drawing a specific molecule. I'm drawing a molecule that fits the following criteria right here and then right here. Okay. And so in both cases, I did satisfy the criteria provided. Okay. Okay. So we're told here monosaccharides tend to be sweet tasting, but their relative sweetness varies a great deal. These are polar, right? Why are they polar? Let's go back and look at this. I'm going to highlight all the polar bonds. This bond right here is polar. That is polar. OH is polar. This is polar. The OH here is polar. And then while we're here, we do have hydrogen bonding for this. We do have hydrogen bonding for all the OHs, right? And hydrogen bonding. So we have both dipole-dipole, which usually stands for molecules that are polar. And then we also have hydrogen bonding. So dipole-dipole here. Here I have just dipole-dipole. Of course, you know, if you have dipole-dipole, you also have LDF. If you have hydrogen bonding, you have LDF and, of course, dipole-dipole. We know they're polar. We know they have high melting points because they are polar and have hydrogen bonding capacity. So their boiling point and their melting point will be very high. The presence of so many polar functional groups capable of hydrogen bonding makes the monosaccharides very water soluble. Yes, for any molecule to be water soluble, so I'm going to say here, for any molecule to be water soluble, which is something we learned before, it must be polar or have hydrogen bonding capacity, or both. It's better when it has both behaviors, right? And usually if it's polar, if it has hydrogen bonding, then it's also polar, right? So I should just say this, right? Because technically when it has hydrogen bonding capacity, it's also polar. So yeah. Okay, so it says right here, Rank the following compounds in order of increasing water solubility. Okay, we're trying to make sure it dissolves in water. Technically, what we're looking at right now should be water soluble, right? Oh, okay. So rank the following compounds in order of increasing water solubility. I don't know why this copied twice. Anyway, we're dealing with glucose. This wasn't written out. We don't see the structure, but seeing the OSE, we know it's a sugar, right? So being a sugar, it's going to be water soluble. And not just water soluble, very water soluble. Let's look at the rest of them. This has a hydroxide, right? Having a hydroxide, it can hydrogen bond, okay? That means it has dipole-dipole and it has London dispersion force. Technically, sugar is a polyhydroxy, right? This one is just a monohydroxy. This is a polyhydroxy. So technically, it has hydrogen bonding capacity, dipole-dipole, LDF. All the intermolecular forces we talked about are seen in that structure right there. Hexane is LDF only, right? So this is the rationale. Sugar is polyhydroxy, so it's very water soluble. Okay. Now we're moving on and talking about this new way of drawing the structures. So this is called a fissure. I didn't mention this before, we hadn't gotten to it, but the way this is drawn, the vertical way of drawing the sugar molecule is called a fissure projection. I actually had, I think it was a co-worker who teaches chemistry who said the easiest way to remember the term fissure projection, the way the bonds are arranged, it looks like if you held a fish up like that, the bones of a fish. And I was like, wow, people are creative. Anyway, right? Minus the fish, what you have left behind, fissure projection. I was like, that's an interesting way of remembering this. But yeah, essentially, that is the fissure projection. So we want to be aware of the fissure projection and that most monosaccharides are drawn this way. Okay, so all carbohydrates except for dihydroxyacetone have one or more chirality centers. Let's see. Oh, there it is. No, this is D-glyceraldehyde. Dihydroxyacetone. Let me go back and see. Is this shown down here? No. Let me go all the way back here, and we'll see that. Dihydroxyacetone. That was the first one we looked at, right? So that will not have, oh yeah, this is not chiral. It doesn't have 4 bonds. Doesn't have 4 bonds, right? To be chiral, the carbon has to have, I should say it doesn't have 4, let me be more specific, single bonds. It does have 4 bonds, but it has to have 4 single bonds. And each group has to be different. It does have 4 bonds, but the bonds are not single bonds, right? 2 are grouped together to make double bonds. And then these groups are exactly alike. So the hydroxyacetone is not chiral. Now we're moving on and looking at glyceraldehyde. Let me scroll down here and see, where was I? Okay, so with this one here, we're told here, because glyceraldehyde is chiral, we have the naturally occurring isomer, which is the D form. And we'll talk about the D form later on. The D form, essentially, when you look at this last group right here, the carbon next to the bottom carbon, if the OH is on the left, it's called the L form. So this is called the L form because the bottommost carbon, the bottommost chiral carbon has a OH group on the left. I know what I'm trying to say. I'm just trying to find a way to communicate that. So you want to look at this carbon right here. This carbon is not chiral, just so you see, right? This carbon is not chiral because when I spread it out, when I draw all the bonds in, the bottom carbon will have 2 hydrogens, right? And then 1 hydroxide, and then it will have the rest of the molecule right here. These 2 are alike. For that reason, the bottommost carbon is not chiral. The chiral carbon is this one right here. So you look at the chiral carbon and ask yourself, there should be a hydroxide group. Is it on the left? So when I was a student, I said, oh, left hydroxide goes with L. The right hydroxide is just not L, so it has to be D. And they use L and D that has to do with what how the molecule rotates that plane polarized light, and we'll get to that later on. Okay. And so L and D tells you the direction in which this chemical, when it interacts with a specialized light, it will rotate that light. Okay, so here we have the chiral carbon with the hydroxide on the right, so that will be D. Okay, the naturally occurring isomer is this one here, and then the unnatural one is the mirror image. So when you find this in nature, you will find the natural one, which is the one on the left. So let me go ahead and move on. Remember, chiral carbons have 4 different groups. So we're told here, like I just mentioned, the prefix D is used when the hydroxide group is drawn on the right-hand side of the carbon chain. It's not just any carbon in the carbon chain. It has to be the chiral carbon that's the bottommost chiral carbon, okay? And then L is used when the hydroxide is on the left-hand side of the bottommost carbon. So the Fisher projection here looks like this. Just take the dash and the wedge structure. The vertical, you just draw a vertical line. The horizontal, draw a horizontal line. And then the part where the lines intersect, that has a carbon in it, right? So much easier. So weird enough, right? People who love organic chemistry don't really like biochem that much. It's not as challenging. It's not really a puzzle necessarily to figure out. It's more informational, a little bit of chemistry here and there, but a little bit more biology, a little bit less chemistry. So it's a little different, okay? But let's look at this. So we're looking at monosaccharides with more than one chirality center. Glucose has 4 chirality centers. Let's see. Definitely not this one, right? Because we have a carbonyl group there. You have to have 4 single bonds around the carbon. This one here is not chiral. Why? Once again, it has 2 groups that are alike. So the carbon cannot be chiral. To be chiral, the carbon has to be surrounded by 4 single bonds, and all groups have to be different. So in our glucose molecule here, we have four different chiral carbons, and these are all highlighted here, as you can see. What I like about this section, they make it so easy for you, right? In the Fisher projection, right there. Here are your carbons. So all you have to do is, I'll use a highlighter for this carbon here. This is 1, 2, 3, 4 groups. And if you can examine it real quick, they're all different, right? Okay, I'm going to move on. For this next one here, 4 different groups. This is a group, this is a group, this is a group, and this is a group. I'm going to do this only one time, okay? Okay, we're trying to make sure, we're trying to confirm what they said. For this one here, once again, this is a group, and then a whole group down here. And they're all different from each other. Then finally, we have this over here, a group, and this whole thing is a group. So as long as the carbon is surrounded by 4 groups, that carbon is chiral. So we can see here we have 1, 2, 3, 4 chiral carbons. And this is glucose. Okay, now I mentioned this before, but now they're showing it to you. The configuration, the L and D, dextrorotatory, levorotatory. This is just telling you once again how this sugar, when it's dissolved in water, and then the specialized plane polarized light is passed through, how this sugar will rotate that light. So once again, on the left here, we have the D sugar, and then the L sugars on the right. Please notice for the most part, D and L are mirror images of each other. Okay, of each other. The rest of this molecule is left like ambiguous because they're going to define it later on, but they're telling you to define the L and the D, you have to look at the far bottom, the bottommost carbon that's chiral, and then you judge it based on the position of the hydroxide. Okay, hopefully this is straightforward. Okay, so for this one here, for each, right now you're like, oh, this, hopefully you're feeling that way, right? Kind of a break. Label all chirality centers. So, of course, I'm going to go back and forth as I'm talking through this. In the life of a chemistry major, organic chemistry is the prerequisite for biochem. And hopefully, by you guys sampling these courses in this course, you're seeing how one feeds into the other, right? By us going through organic, now we know what all these terms are, chirality and things like that, and enantiomer, which just means mirror image. Okay, so label all chirality centers. Okay, well, this one here, this one here. Simple, right? Remember, this is disqualified by the two hydrogens. This one here is disqualified by the double bond. So I've done the first one here. This, and this. I've done number one. Classify the monosaccharide as D or L, okay? Let me find the lowest chiral carbon right here. Okay, this is on the right, so it's gotta be D. D right one, no, not really, that's not how you say it. And then this one on the left, so it has to be L, right? Simple enough. When I got to this section when I was in class, I was smiling. I'm like, whoa, this is like taking a break. Draw the enantiomer. Whoa, okay. So to draw the enantiomer, remember the enantiomer is the mirror image, right? So it's like enantiomer. Let me see. I'm going to draw this right here. Let me erase all the markings that I have here. And then for this one here, my mirror image will be on the right. So this one here, this is my what? My D isomer or D enantiomer. This one here is my L. So I have to draw L for this one and I have to draw the D for that. Okay. I will start by drawing my lines, my fish bones, CH2, OH, CHO. That part doesn't change. For the middle part, I just flip it over. So I put my OHs on the left and then my H's on the right. Not bad, huh? Not bad at all. Okay. On this part here, oops, if I can just draw this. CH2OH, CHO, once again, the top and the bottom part is the same. Now I have to draw 3 lines, 1, 2, 3. And then here, HOH, H, I'm just trying to copy this part here, right? Then on the other end, OH, H, OH, right? So I'm going to highlight this. That explains why we have D. And then, of course, this explains why we have an L here. And then this goes with that. This goes with that. Okay. Oh, wow. Okay. We have a little bit more work here. Let's see. For each type of monosaccharide, it says, give an example of a D sugar. Ooh, to the right. And then label each chirality center. Okay, we'll do both of these. And aldopentose. Okay, let me copy this. Okay. So I'm on an aldopentose. That's a D sugar. Aldo again, carbonyl as my first carbon. Pentose, I have to add 4 more carbons. 1, 2, 3, 4. I probably should write a little smaller. CH2OH. Okay, they said that they all have to be D sugars, right? So my bottommost OH has to be on the right. And then that means on the left I have H. I can make this here like that. The criteria was on this one. I had to fulfill this criteria here, and then of course that criteria here and the number of carbons. And this would be my first one. My second one is what? A ketohexose. I won't do the tetros because it's very similar to the ketohexose. I'll just do this one here. Paste. Why did it paste the same thing? Okay, hold on. Let me copy this again. Something happened to where it didn't copy. Okay, so like before, this time I have my first carbon CH2OH. So it's a hexose. I need 5 more carbons, right? Carbonyl carbon second, third, fourth, fifth, sixth. Okay, so this here has to be on the right to fulfill their requirements. The rest I can do whatever I want. I'll put these both to the left just because. There. I have 1, 2, 3, 4, 5, 6. That part is done. It's a sugar. I have my ketose group right here. I have this on the right. I'm done, right? So I'm not going to work on this one here because y'all can see it follows the same trend. Okay. So we're being told here all naturally occurring sugars are D sugars, okay? So that's the case. Even though you can draw it on papers, the natural sugars are the ones where you have your hydroxide, the farthermost, yeah, the chiral carbon that's further down has the hydroxide on the right. So this is a natural D sugar. And then L sugars are usually the unnatural ones. They usually synthesize. Okay, now we're talking about health, right? So these are the common monosaccharides. Glucose, which is a dextrose, is a blood sugar, and it's the most abundant monosaccharides. We usually are told, watch your glucose. Make sure you have a healthy and normal blood glucose. You know, your annual test, if you do have those, the doctor will tell you your blood sugar is normal or it's not normal. You need to work out and stop eating carbs, right? So the hormone insulin regulates blood sugars or blood glucose levels by stimulating the uptake of glucose into the tissues and converts it to glycogen. So in your body, any excess glucose is converted into glycogen and stored in your tissues, in your cells inside the tissues, okay? Patients who have diabetes, sometimes it has to do with an ineffective, maybe not having enough insulin or, yeah, insufficient insulin. And if that's the case, they have to monitor their diet or inject insulin. So in that case, if their body is not making enough insulin, they have to take a synthetic form of insulin. Okay? So I'm trying not to veer too far from the chemistry because our goal is to focus on the chemistry. So these are all naturally occurring sugars, and as you can see, we have glucose, D-glucose, D-galactose, D-fructose. This is the normal sugar that we know about, the blood sugar. This is the fruit sugar right here. And some of this is the milk sugar. We'll get into all this stuff. So we're told here to draw a Fisher projection formula for D-galactose. So I'm going to just take this right here because I can, right? So when the bonds are kind of disconnected, that's in the Fisher form. The Fisher form has to have the bonds or the central carbons looking like, you know, skeletal forms. So I'm going to show you how that looks. Because you're probably asking yourself, why are they asking us to draw this if it's already drawn? Okay. Okay, so this right here is the Fisher form. I'm just going to put the edge pieces right here. I have 1, 2, 3, 4. I'm going to draw 4 horizontal lines. The core of the sugar molecule has to look like a skeletal structure. Then you can put in your OH on the right, H. Nothing complicated. I'm just copying over what I have on the left structure right here. That is not considered Fisher. And that's all it is. This is the Fisher projection. Projection. Okay? The Fisher molecule right here. You have to have the carbons looking like skeletal forms. Okay. Now, oh, okay. They want us to draw a Fisher projection formula for the enantiomer of the D-galactose. The enantiomer is the mirror image. So once we have this is the D-galactose, by the way. Let me see if I can be a little lazy. So if I can copy my picture from up here, because I'm trying to go through this a little faster so the video is not as long. Let me see, scroll down here. Then maybe I can get a mirror image of it. So this is the D-galactose. We're going to be drawing the L galactose on the right, right? So I have CHO on the bottom, slightly larger, CH2OH on the left, and then I'm going to draw 4 horizontal lines. And then I just flip this over, OH, H, H, OH, and then H, OH, OH, H. That's it. Fisher projections for both of these. You have the D on the left and then the L on the right. Okay? So I did both of these as requested. Okay. So now we're moving on and looking at, let's see. We're told that galactose is one of the components of the disaccharide lactose, right? So galactose combines with a different sugar for us to get lactose. Patients with galactosemia lack an enzyme needed to metabolize galactose, which accumulates and causes cataracts and cirrhosis. Ooh. Fructose is one of the components of disaccharide sucrose. So sucrose is the sugar that we eat. That's the sugar we consume. So we do consume a disaccharide, sucrose. One of those sugars of sucrose is called fructose. It is a ketohexose found in honey and almost twice as sweet as a table sugar with the same number of calories per gram. Okay, so before we get into the disaccharides and everything, they want us to make sure that we can draw the cyclical or the cyclic form of these monosaccharides. Here's the thing. While we're drawing the monosaccharides in this form, the vertical form, and the Fisher projection, the reality is when these monosaccharides hit water, when they're exposed to an aqueous environment, they change their form from the straight form or the acyclic form into a cyclic form right here. Okay, and this cyclic form, the Hayworth is called the Hayworth projection right here. Hayworth. Okay, so the sugar will be in the acyclic form, but when it hits water, it reacts, interacts in the water to form the cyclical form. So we're supposed to know how to draw the structure, move from the acyclic form to the cyclic form. Okay, that's our goal right now. I'm going to slow this down just a little bit so we can be comfortable. Yeah. Here that the hydroxyl and carbonyl groups can react together to form a ring. When we are trying to form a ring, right here, the carbonyl group can react with the hydroxide group to form a ring. And so we're told here that this hydroxide group reacts to form a 6-membered ring. This hydroxide here will react with the carbonyl on carbon 1 to form a 6-membered ring. Okay? So this is showing you how we can go from an acyclic glucose into a cyclic glucose. The process is called cyclization. So we're going to make it a cycle, right? The Hayworth projection. The first thing you start with is start with your glucose in the vertical position. And then you want to rotate your glucose 90 degrees. I used to say just drop it to the right. Okay, drop the glucose as is. Let it fall like plank position. Bam, to the right. Okay, so you're going to rotate it this way, if that makes sense. So what I'm going to do here is I'll just say, let me write to you if you're trying to kind of struggling to see what's going on. Left becomes up, right becomes down. So the left side ends up on the top because remember it's falling down like a tree to the right. So the left side becomes the one that's up and then the right side becomes the one that faces down. So just to kind of show you this, all these right molecules, or not molecules, sorry, elements right here, species right here will be the bottom one. So you can see right here, OH, H, OH. Let me use a different color for the left part. I'll use the bright blue. H, HO, H, 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 OH, H. You can see that, right? So it fell on its right side. Okay, now that we can see the visual, now you can see, right? carbon 1, 2, 3, 4. So carbon 1 that's all the way further up now ends up being the one that's further right. And the one that's further down ends up being further left. Now we're moving on to cyclize it. Next, the chain must be twisted around, forming a 6-membered ring. So here's what I'm going to show you. Let me show you the future a little bit, then we'll come back to this step. In the future, which, okay, this has the sides. I'm going to highlight the center part I want you to see. The ring is made up of 5 carbons and 1 oxygen. So hopefully you can see that, right? It's made up of 5 carbons and 1 oxygen. Not all 6 are carbons. So we need to do that too for our ring formation. Let me go back here and show you. Essentially, the ring will contain 5 of our carbons. This will be part of the ring. Ring, 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 ring. So our ring will contain the following elements I have highlighted. Our central carbons, not the last one, from the top one all the way to the last but one. Those are all in the center. And then this oxygen. The 6th carbon ends up being a side group on the ring. Okay? So what happens here is this oxygen is currently, let me zoom in, right? So y'all see this carbon here connects to that, connects to that, connects to that, connects to that, and then this carbon 5 connects to oxygen. Then this oxygen comes back all the way here and connects back to carbon 1. Okay? So let's see how that looks over here. I hate that they already have these over here. Okay. So this is carbon 1, right? They kind of flip it over a little bit the other way around, but you see that, right? Carbon 1 is here, 2, 3, 4, 5, 6. I guess if I want my picture to match theirs, the better way for me to show this would be to show it the other way around. Okay, so they can match theirs. So to say this goes around to attach to this. Okay, so when they're drawing this, essentially you have this structure right here. Carbon 1 is right here. Carbon 2 is right here. Carbon 3 is here. Carbon 4 is here. Carbon 5 is here. Then this end here is oxygen that is in the place of where carbon 6 would be. Okay? And then these two end up attaching together like that. But for right now, let me follow the steps and not get ahead of myself. Now they have gone ahead and put these here. I think it's too early, but that's okay. Remember, everything that's in the bottom here will be on the bottom in this structure here. So you can see this is carbon 2, right? Oops, I pressed the wrong thing. This is carbon 2, this is carbon 3, this is 4, this is 5, and of course this is the oxygen. On carbon 2, the OH is on the bottom. We have OH right here. You can see H is on the top, H on the top. Carbon 3, H is bottom. Carbon 3, H is on the bottom. OH on the top, OH on the top. So once you draw that ring on the Haworth projection, you will now bring in those side groups, the hydroxides and the H's, and you'll put them on vertical bonds in the Haworth projection, okay, like I'm doing right here. And you want to be consistent. Do this for all the carbons, so, except for carbon 1. Carbon 1 will be handled last. So carbon 2, oh, I feel like all these numbers here are just confusing. Y'all saw those numbers, right? So carbon 1 has OH on the bottom. Carbon 2 has OH on the bottom. That's this one right here. Carbon 3 has OH on the top and H on the bottom. Carbon 4 has OH on the bottom, OH right here, H on the top. Carbon 5 has OH on the bottom and H on the top, right? So for this one here, carbon 5, I can't really even write the OH here. I'm running out of room. Remember, the OH from carbon 5 is right here. So on carbon 5, let me see if I can make this a little smaller. Man, this is a struggle. This carbon right here, let me make the bond a little smaller. On carbon 5, this ends up holding a certain position, and then this ends up being the other. So these ends up being the two side groups on carbon 5. So on this structure here, the CH2 OH end up being on the top, and then the H is the one on the bottom right here. Okay, now we have to connect this one here and then bring in its top and bottom. So in the structure down here, they connect the first carbon, then you have an OH on the bottom or OH on the top. For you to know where your OH is, they have to tell you, okay? When you're cyclizing, when you're taking your sugar molecule from a linear form to a cyclic form, they will have to tell you whether you're drawing the alpha anomer or the beta anomer. Okay, so all the two sugar molecules, if the OH is on the bottom, this is called alpha. If the OH in the cyclic form, 4 carbon 1 is on the bottom, this is called alpha. So the OH position here ties into this designation. If the OH is on the top of the ring or coming out from the ring, this is called beta. Okay, remember the rest of the OH positions here have to follow the original structure. This one here is based on the designation that they tell you when they're telling you what to draw. This CH2OH usually ends up on the top. It's most commonly on the top. Okay, so we're gonna get a chance to draw this over again so you can see how this works out. But once again, let me go over this again because I know it's kind of a weird process, right? Take your acyclic sugar, recognize that all the left species will end up on the top, right? And while I'm here, I'll just say this one here will also be on top. For the most part is on top. Remember, while we're here, the ring is going to be made up of carbon 1, 2, 3, 4, 5, and oxygen. That will be your ring structure right there. You will drop the whole molecule to the right. Everything that's on the left ends up being on top. Everything that's on the right ends up being on the bottom. You can go on from here and draw the core ring structure, and then based on what they tell you, you can go ahead. Of course, these get added in as is, right? You add this as is, add this as is, add this as is. You can't just add this as is. In a way, you kind of, for this part here, you switch positions, right? It looks like the OH is here. You put the H is here, then CH2OH. So it looks something like this, right? In the organic book, they do a little bit better job than they do right here. They actually had them rotate this first before they actually draw the structure. So I might add that into, I just remember that, I might add that into this to make it a little easier. So what I'm saying here, even though it wasn't listed in the steps, I'll just say this. When you have this in this form, you can go ahead and rotate it if it's a lot easier for you. Because my goal is to help you guys do this. If you rotate it, rotate this once this way. Put this over here, put this up, and then bring this down. So this remain as CHO, C, 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 C. So this is carbon 1. This is carbon 2. I'm going to write this in the bottom right here. Okay, trying to make this easier, carbon 1. So carbon 1, it just remains like that. Carbon 2, we have OH on the bottom, H on top. Carbon 3, we have H on the bottom, OH on top. Carbon 4, we have OH. Oh, no, carbon 4 is where we're rotating things, right? Once we rotate things in carbon 4, 1, 2, 3, 4. Oh my goodness, did I mess up? This is carbon 1, 2, 3, 4. I guess I was right with this one here. Okay, on carbon 4, I do have OH. I was right. I was looking at the wrong thing. Carbon 5 is where we have the rotation, right? We have the H on the bottom, we have the OH over here, and then we have the CH2OH. Okay, finally got it right. Finally, took a couple of tries here. Okay, so your ring will involve the following. This carbon here, this carbon here, this carbon here, that carbon, and that oxygen. Okay, and once you draw it out, you see how this works out. So let me go ahead and since I've done this structure right here, let me add a page and just redraw the structure I already drew from this part here. So once we have this, what I usually do to make my life simpler, I just draw the core. Unlike what they did, I put my oxygen here. This is my carbon 1 position. This is 2, this is 3, this is 1, 2, 3, 4, and this is 5, right? This is carbon 1, this is 2, this is 3, this is 4, this is 5. So carbon 1, I will label that last, depends on what's going on, right? This is carbon 1. Carbon 2, I know I have a OH on the bottom and I have an H on top, so this part is done. Carbon 3, I know I have an H on the bottom, OH on top, this part is done. Carbon 4, I know I have an OH on the bottom, H on the top, this part is done. Carbon 5, I have an H on the bottom, CH2OH on the top. So now by doing this, I have all these done. This O here is pretty much this O right here, so that's done too. Now for this carbon 1, you always do that one last, right? As I mentioned, they will tell you either draw the alpha or the beta. If I put the OH on the bottom and the H on top, this is my alpha ionomer. And that's it, okay? So if it helps, rotate these and then draw them in there. And hopefully that made sense. I don't know why they skipped the rotation part in this book, but yeah. If you're asked to identify alpha or beta, look at the OH. This is beta ionomer. This is alpha ionomer. So much easier, huh? So here they're showing you how in water the sugar molecule actually goes from the alpha ionomer to the beta ionomer. It kind of goes back and forth, okay? So you're seeing here that we have 37% of the alpha isomer and then 63% of the beta isomer. So we have more of this than this. And the most likely, if you're wondering, might be elements are very introverted in a sense that elements tend to like their space. And so you see how the OHs are so close to each other here. So they would rather kind of be staggered. So you can see that we have more of this isomer because this one here has the OH staggered. And so they can kind of spread out and occupy space that makes them comfortable versus shoving two large molecules very close to each other. When I was a student, I used to think it would be like, you know, having kind of bigger people sitting close to each other in a very tiny seat, something like that. But yeah, elements tend to like to be spread out and be far away from other elements, even in a compound if that's possible. That's the whole premise of Vesper model, right? Bonds and elements do the same thing. As long as you have electrons, you have the behavior of preferring space. Okay, draw the cyclic form of monosaccharide. We've done that before, right? So we're going to be drawing the cyclic form of D-galactose. Ooh, okay. I will do it from right here. We're going to be doing the little flip thing and do all that stuff. Let's see if we can draw our own. We will draw our own, then we'll match ours with theirs, okay? Let me start with this. I'm a little rusty on these because I have to multitask. I know I'm still working with you guys, but I'm already preparing for my next semester. I thought summer 1, which starts next week, I thought my class wasn't going to make, then I found out yesterday it's going to make, so I've been a little preoccupied. Oh, the life, y'all, the life. So yeah, our class ends next week, and then as soon as it ends, I have another class that starts. It's exciting. It's exciting. So my syllabus, they changed the modality. It was supposed to be hybrid. Now it's face-to-face. So I've been working on my syllabus, trying to plan things and stuff like that. Anyway. Okay, so let me scroll down. Okay, let me drop this to the right, okay? I'm going to drop this to the right, so I'm going to have 1, 2, 3, 4. You know what? Before I drop it, let me move this over. So I'll do the little rotate first, then drop. Move this way, move this that way, move that this way, then drop. So when I drop it, I'll have O, C, 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 C. So O with 5 C's, okay? O, H, C, 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 C. 1, 2, 3, 4, 5. Oh, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so I've already rotated here, right? So this has to go up. This has to go up like that, CH2OH. And then this H has to go down. Okay, I want to deal with that, get it out of the way first. Okay, so this rotation is done. I've copied that over. And this, by the way, is to number this properly. 1, 2, 3, 4, 5, right? So I've moved this over here, moved that over there. This is my carbon 5 right here. This is 4, 3, 2, 1. Carbon 1 is CHO. Carbon 2, I have OH on the bottom, H on the top. Oh, I forgot to mention this. Left, up, right, down, because we're still learning, right? Left, up, right, down. So this is going to be on the bottom, followed by that, followed by this, and this already got flipped over, right? So this is H on the top, so this part is done, this part is done. OH on the top, this part is done. And then I have OH on the top here, this part is done. So everything is done so far. Okay, next thing, I'm going to draw my core, the ring itself. So for the ring, I'm going to have flat, flat, and then this, this. So it's a six-member ring that's kind of lying flat, right? And then over here, this doesn't work very well. That's okay. Over here, I put my oxygen in here, right, on the side. And then this becomes my carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. Okay? Carbon 1 I'll do last. Did they say what kind I should draw? Oh, I can do both. Ha, you know what? Let me copy this while I'm here. I'm going to be lazy. I'm going to be innovative, as my students said, and then draw this one on top of the other. There. Okay, so for this top one here, this is carbon 1. I'll do that one last. Carbon 2, I have to have OH on the bottom, H on top. This part is done. Carbon 3, I have to add H on the bottom, OH on top. Carbon 4, H on the bottom, OH on the top. Carbon 5, CH2, OH, and then H. Ooh, connect. Y'all see that, right? This. Let me make this a little higher. It's almost sitting on top of that one. Now I'll choose to make this first one alpha anima. So this would be my alpha D galactose. Is this D galactose? Yeah. Alpha D galactose. Okay. Second one, I'll just copy everything. Man, I'm bringing these close. They don't like being close to each other. OH, H, OH, H, OH, H. I just copied everything, doing this part last, flip this over. And this would be beta-D galactose. Okay? Yeah, so they go through, they draw this, they draw that. They do a much better job in this part here. Yeah, so let me see. Yeah, in my alpha, the OHs were next to each other. So this is an alpha isomer of cyclic D-galactose. And then, was that it? Oh, okay. Well, they chose the alpha. You saw how we can do both, right? Okay. We're now moving on and trying to get the cyclic form of a ketose. We've been doing aldose so far. Now we're doing ketose. The thing with the ketose, though, is the carbonyl carbon is an important part of the ring. So that's tricky. For that reason, ketoses, like fructose, form 5-membered rings, not 6-membered rings, with 2 isomers. Of course, we saw the alpha and the beta form. Okay? So this is how this happens. As before, you have this one here, carbon 1, 2, 3, 4, 5, 6. You still have to cyclize this like we did before. Bring this up, bring this down here, like we did before. Okay, let me see. So once you bring this down, we have 1, 2, 3, 4, 5, like we did before. Let me see if I can write this right here. 1, 2, 3, 4, 5. The difference here is we have a carbonyl carbon right here, right? And then we have a CH2OH for carbon 1. This is our carbon 1, carbon 2, carbon 3, carbon 4, carbon 5. In our carbon 5, we move things around. So we have a OH right here. We have a CH2OH. And then we have a H on the bottom. On carbon 4, we have a OH on the bottom and an H on top. On carbon 3, we have H on the bottom and OH on top. Okay? So let me see how they work things out here. It's a little tricky with this one. So I'm just going to show you how we do the 5-membered ring first, and then we'll deal with this last, just because I feel like it's less overwhelming that way. Because when you look at this, it looks like they've already done it, right? It's done. Like, this is the middle, supposedly. How do we jump from here to that, right? I feel like they skipped a lot of steps. But just like before, this time our ring involves this, 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 and this. Okay? And to try to keep with the convention we had before, our first carbon is the one over here. And then this becomes our oxygen. So the oxygen we have here is over here. So just like we did before, and then remember how we had our first carbon? Our first carbon technically is going to be this one here. In the ring, this is our first carbon. So they write it here as carbon 2. I guess let me stick with that convention. With the ring, I'm adapting to them whenever I think is better. So we have it here as carbon 1, carbon 2. So in the ring, our ring is made up of carbon 2, 3, 4, 5, and then that. So I write here carbon 2, carbon 3, carbon 4, carbon 5, and then we have this. So in carbon 2, I will deal with this last. I'm not the best at drawing these pictures. If you're not good at drawing, don't feel bad. You can see how horrible my structure is. On carbon, I'll start with carbon 3. With 3, I had an H on the bottom and an OH on the top, right? So I'm done with this part. With 4, I had an OH on the bottom and an H on the top. So I'm done with this part. With 5, I had a CH2OH on the top, this part here, and an H on the bottom. So I'm done with that part. This is part of the ring, so this has been handled. I'm going to do the first one to the right last. With this one here, we don't have a OH group. Well, sorry, we do have a OH group, but it's not paired with an H. It's paired with a CH2OH. So, depending on what animal you're drawing, you can have the CH2OH on top, and then the OH on the bottom for dealing with the alpha animal. We're always tracking the OH of the first carbon to the right of the oxygen, and that makes sense. This carbon right here. If this is on the bottom like we have over here, that's the alpha isomer. If you flip this over to have the situation here, that's the beta isomer. Once again, we're looking at the carbon to the right of the oxygen, and we're looking at that only, okay? So remember, here in the place of H, we have CH2OH, and it's always paired with hydroxide. Okay, there are more chemical reactions that explain how the carbonyl becomes hydroxide and stuff. We are not required to cover those chemical reactions. All we need to know is what happens in the end, okay, versus all the steps. Okay. Oh, I left the 3 questions here because all we're doing is labeling each compound as alpha or beta isomer. Once again, look at the first carbon to the right of the oxygen. That's this one here. Where's your hydroxide? On the bottom. On the bottom will be alpha isomer. And then here, alpha isomer again. And then here, beta isomer. I'm just using that position. That's it, to figure out what kind of isomer I have. Okay? Because that's the only criteria that is used to determine the type of isomer you would have. Now, if they gave you the name, then you add the alpha to the rest of the name. Okay? Oh, well, that was a little fun, right? Now we're moving on and talking about chemical reactions. With chemical reactions here, we're looking at some reactions that the glucose or the sugars undergo. I actually skipped some of these reactions with the organic part because I felt like we're getting too many reactions and it was getting overwhelming. So I skipped some of these then, but we're seeing them here. They are relevant to this section. The carbonyl carbon can react with hydrogen, and the name of this reaction, the generic name of it, is reduction. Reduction is the opposite of oxidation. So let me define this somewhere. Reduction involves adding hydrogen. Okay, it's the opposite of oxidation. So I'll say here it is the opposite of oxidation. In the world of organic chemistry, oxidation is usually adding oxygen, and then reduction is adding hydrogen. Okay, and there's more to it than that, but once again, I'm keeping it simple because of how deep we're going in this class. So that being the case, if we know that we're adding hydrogen, when you're adding to a double bond, a bond has to break. Even in the organic section, we're adding to a double bond, I shouldn't say the double bond, a second bond. How about that? A second bond must break, because technically both bonds are not breaking, just the second one, the redundant one, or the seemingly redundant one, because it's not redundant at all. Okay, so what we're seeing here is one of the two bonds of the double bond will break to accommodate the two hydrogen atoms that are coming in. So the hydrogen atoms are bonded to each other, right? Their bond breaks, and when their bond breaks, you have free hydrogens available to mingle. The second bond between the carbon and the oxygen here breaks. So when it breaks, you have a part of the carbon and the part of the oxygen available to mingle with the hydrogen. So these form bonds here, and we end up with this. So when you consolidate it, you end up with this, CH2OH. Okay, so what they're saying here is you can essentially go from the aldehyde to an alcohol. Okay, so this is a D-glucose, and this can be reduced using palladium catalyst to form glucetol or glucetol. And this is called sorbitol. This is a more common name for that. Okay, and so there's an application for this down the road, and we'll see that down the road. Okay, so just like you can reduce, let me summarize this right here. Sugars can be reduced to form alcohols, right? At least we're talking about this part here. It got reduced and it formed an alcohol. And I'm going to go down here and see, now we're doing the opposite. We're oxidizing it. The reagent we're using here is a reagent that fits. We're trying to use an oxidizing agent that's not too strong. Different reactants have different strengths of oxidation. We're trying to use one that will target only this group here and leave the rest of these groups alone. We don't want them touched. Okay, so Benedict's reagent is a reagent that will do that. We're not doing this in the lab, but I think, no, I don't think I did it for your carbohydrates lab. Yeah, if we were in the lab on campus, we would have done this, right? Add the sugar to the copper solution and then boil it, and then it will turn brick red as it makes the copper oxide. And then we'll know for sure our sugar was oxidized. Bottom line, in this case here, if you remember back to the aldehyde, I want to say in 1411, no, wrong class. Last week or sometime this week, we talked about this where we said that the alcohol, the primary alcohol, we mentioned this before, the primary alcohol can be oxidized to aldehyde, right? When we mentioned this before, essentially, now we're picking up from the aldehyde, which can be oxidized further to form the carboxylic acid. The information we learned in the organic portion, at least this part here, applies over here. If you have an aldehyde, you can oxidize it. What happens here is the oxygen goes right between these two right here, and you get a carboxylic acid. So an aldose sugar can be oxidized to form a carboxylic acid. So glucose can be oxidized to form what is called gluconic acid. That's the oxidized version of D-glucose. Okay, so here, oh, okay, that's okay. I have two of these. One, I really thought I had an aldose and the ketose. It's okay. I just work on one of these because it is similar, right? The only difference we have here is the size of the sugar. I'll just work on one of these. What compound is formed when each aldose is treated with hydrogen in the presence of palladium catalyst? So right here, I'm going to draw this out so we can see how it looks. And then I have 1, 2, 3, 4, 5 additional carbons. 1, 2, 3, 4, 5. 1, 2, 3, 4. No, 5. I'm drawing this first one here, right? 1, 2, 3, 4, 5, 6. Yep, 6 sugars. So down here I have CH2, OH. I have OH on the right, H, H, OH, H, OH, OH, and then H. Okay, so I'm adding hydrogen, right? So I'm going to write here hydrogen in the presence of palladium. You can write it that way. I know ultimately I'm adding the hydrogen here and here, right? So when we form the product, I'm going to consolidate. It'll be CH2, right? Because this is where I'm putting them, right here and then right here. So CH2OH, that would be my first carbon. Then 2, 3, 4, 5, 6, CH2OH. And then let's see if I can remember this. On the right, OH, H, H, OH. On the left, H, OH, OH, H. That's it. Okay. I'm following a pattern, right? Usually the middle part of the sugar, one side is an H, the other side is an OH. So I'm trying to follow the pattern, right? You get something similar for this right here, where the aldehyde will become an alcohol. Okay, so finally we're now dealing with the disaccharides. This is pretty much the end of the monosaccharides. We're not going any deeper than that. Disaccharides are carbohydrates composed of 2 monosaccharides. We're told here with the disaccharides, you have 2 monosaccharides bonded together, and the bond they're using to stay together is called a glycosidic linkage. Glycose from glucose, sugar, and that's your linkage right there. And these two sugars, glucose and glucose, attach together to form maltose. Okay, so back here. A disaccharide is formed when a hydroxyl group of one monosaccharide reacts with the hydroxyl group of a second monosaccharide. Okay, so we can see this was an alpha, right? Because the hydroxide was in the bottom right here. And then this one here is another alpha. Okay, so from carbon 1 and carbon 4 right here, a reaction took place. Okay, so I think they'll show us what happens. No, they don't. They show it in the organic version of the book at least. Okay, so what happens here? I'm going to show carbon 1 and carbon 4. Let me draw it on the bottom here. Dehydration happens. Okay, so my focus right here is what's happening between carbon 1 and carbon 4 of these adjacent sugar molecules. Okay, so this is what's going on. This one here has an OH on the bottom and it has an H on the top. And this one here has, based on what we have, an H on the top and an OH on the bottom. Okay, it's a dehydration synthesis. That means that dehydration synthesis, that means that to make it, you have to lose water. Okay, so to make the disaccharide, water must be lost. So how about this? Water, H2O, is essentially one H and an OH, right? An H and an OH make water. So sometimes we write water as HOH. So what I'm going to do here is I'm going to take the H from here, combining with the OH from here. Then they go off together. So on the side somewhere here, H2O is formed as these go off together. Well, what happens now? So now this carbon is like, well, I used to be attached to an OH, but I don't have anything else to be attached to. And the carbon here is like, well, you can attach to my oxygen. So let's share my oxygen. Bam, right there. And this is called the glycosidic linkage. Okay, so dehydration synthesis once again means in the making of the compound, a water is lost. So if these got together because the water was lost, you can break them apart by bringing in the water. The thing that was lost that brought them together. So it's their loss that drove them together. Once you supplement that loss by bringing back the water, you break them apart. They have no reason to stay together anymore. This is not personal, this is chemistry. Oh, anyway, so moving on. When this reaction occurs, disaccharides, we'll continue to talk about that, right? When this dehydration synthesis occurs between two monosaccharides, the bond that joins the two rings is called the glycosidic linkage. And we have all these different linkages, right? Once again, here we don't see a side-by-side combination like we saw up here, right? So when I was trying to learn this, right, I mean, y'all see my mind as a grown adult. When I was a younger grown adult, my mind was even more wild than it is right now. I saw this as two molecules holding hands. Okay, it's like they're holding the oxygen together, and their hands are kind of, swinging low. So you have two molecules because the bond direction matters. We're going to be identifying that later on. The bond direction matters. Okay, so the two molecules are such that their hydroxide allows them to form this type of glycosidic linkage, versus this one here. Where the hydroxides are makes them have a different kind of glycosidic linkage. It's still glycosidic, but it's different. On this one on the left, the hydroxide was on the bottom, right? On the one on the right, the hydroxide was on top. So they can't have that side by side, like two people holding hands and swinging, maybe a kid in the middle of them. They have to have a top and bottom glycosidic linkage. It all boils down to where the original hydroxide was. Okay, so we're going to be classifying our glycosidic linkage like it says so right here. In a glycosidic linkage, joining the two rings can either be alpha or beta. We're back to the alpha beta designation. Okay, well, if you have two sugars though, or two Hayworth projections, which one do you use to decide alpha or beta? They tell you the one on the left. They didn't say it, but you would have to imply, because chemists are not the best communicators. Oh, I hope we're not having a meeting. Come on, people. Okay, anyway, the one on the left is the one that they use to designate it. So even though we have two sugar molecules here, or two carbohydrate molecules, the hydroxide, the original hydroxide group on the left is the one that will be used to designate this. Okay, the one on the left, before this bond was formed, the hydroxide group was on the bottom, like that. For that reason, this will be alpha. Okay, and the way to describe this bond is very interesting. We know it's a glycosidic linkage. Two glucose, or not glucose, but two sugar molecules are tied together, right? But this is how they write it. So I've seen alpha 1, 2, 4, alpha dash 1, 2, 4, or I'm going to go the way they have it here. I'm going to stick with what they're doing, which is 1, 2, 4. They're saying this is a glycosidic linkage, right? A bond between two sugar molecules or two carbohydrates. And these sugar molecules are connected via the first carbon for the molecule on the left, the sugar molecule on the left, the fourth carbon for the sugar molecule on the right, and the sugar molecule on the left had a hydroxide group that was facing downwards, ergo the alpha. So now we're having these biochem people trying to act all organic like, right? They're now becoming a little bit more technical with the dashes and the arrows and all the details, right? So we want to follow that convention. Carbon 1, 2 carbon 4, but they don't say carbon, they say 1, 2, 4 dash alpha dash glycosidic linkage. And that's what that means. Okay, so here we have a different, right? A different arrangement. This time, our sugar molecule on the left is the one that has the facing up hydroxide. So since it has the facing up hydroxide, this is called a beta linkage, a beta glycosidic linkage. So once again, we have the carbon right here, the original carbon 1 for the sugar molecule on the left had a hydroxide group facing upwards. That's why it's beta. Carbon 1 for the sugar molecule on the left forms a bond with carbon 4 for the sugar molecule on the right. We don't care where the hydroxide group on the carbon on the right was. All we care about was where it was on the left. But we know on the right side it was in the bottom. How do we know that? For the right molecule, because you see how it attaches, it sits up versus on the side. Yeah. That means the original hydroxide was right here. For this one, for the bottom one, it was right here. Okay. So hydrolysis is the opposite of dehydration synthesis. Hydrolysis, like I mentioned the day before yesterday, lysis is break up, and then hydro with water. If we want to break these up, digest them, metabolize them, just not have them together, we just have to use water to break them up. And when we add water, it cleaves the CO glycosidic bond. It breaks this bond right here and returns them to their original monosaccharide form, the form they were before they got together. Okay. So here they're showing you what's happening. So you want to be able to go from the pair to the individuals, right? Ergo, when I was saying, hands holding, these two are holding this little element right here. Based on this, the products will have, of course, this O can go with well, in this picture, apparently this O came from the one on the left. But yeah, this O goes back with the molecule on the right, and then the molecule on the left. Once you add water, you're adding H and OH. According to them, OH goes to this carbon right here, H goes to that. And we end up with this right here. You see how the H from the water came there. So we had H and OH right here and here. And essentially water is added in the hydrolysis and breaks them apart. So we go from maltose to 2 glucoses. That's not really a word, but 2 glucose molecules, right? Okay, so let's talk about lactose intolerant. Ooh, lactose intolerant. Why lactose intolerant? Why? You gotta be a thing. Okay, lactose is a disaccharide in milk. It consists of galactose, at least 1 galactose and 1 glucose. So together, galactose and glucose make lactose. And they're joined by a 1,2,4 beta glycosidic bond. So you can see right here, carbon 1, on the left molecule, the galactose, carbon 4, yes, carbon 4, this is 1, 2, 3, 4, this is carbon 1 right here. So carbon 1 on the galactose, carbon 4 on the glucose, these bond together to make lactose. So essentially, lactose is galactose plus glucose, and they're attached together, right? Disaccharide, and then mono and mono. Okay, and these are attached together by a beta glycosidic linkage. Well, oh, they didn't finish the story. Of course, if you have that as an issue, usually if you cannot process lactose, that's usually an enzyme that is not, either you don't have enough enzymes or the enzyme is not able to break up this bond. But the goal of the enzyme is to break up that bond right there, right? Okay, here. This chapter wasn't that bad, right? We're not too far from the end. So here you're told to locate the glycosidic linkage of cellobios. Oh, they get to it right here. Okay, I was like, I felt like they didn't really finish the story. Glycosidic linkage is right here. Let me zoom this in so y'all can see. Is that linkage right there, okay? Number the carbon atoms in both rings. Okay, we can do that. So we number the first one, number the carbons, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay. Done. Classify the glycosidic linkage. Okay. Since this one here, if I try to redraw the is facing up, so it's going to be beta glycosidic. To be more formal, I can say 1, 2, 4 dash beta. If I mention, yeah, 1, 2 form dash beta. That's it. Done. Okay, so back to the story. Disaccharide bond is cleaved by the enzyme lactase. Individuals who are lactose intolerant no longer produce this enzyme. So you can supplement it, or you can just say goodbye to cheese and all these fun foods, right? Without the enzyme, lactose cannot be digested, causing abdominal cramps and diarrhea. Okay, moving on. Sucrose, this is table sugar. It's a disaccharide containing 1 glucose and 1 fructose ring. This is sucrose right here. Okay, you can see. So with this part though, it's kind of tricky. Which is the molecule on the left? Because they're both like they're vertically oriented. So which one is the one on the left? Okay, it's a little tricky. So sucrose is a very sweet sugar. It's very sweet, but contains so many calories. So to reduce the caloric intake, many artificial sweeteners have been developed. Once again, my business majors, y'all, they come in here and they made sucralose. Okay, so for us to compare these two, I'm going to copy this so we can have them side by side. Because there is some chemistry in here, but the point is to trick the body to not metabolize it, to have the essence of all things sweet. But how do you trick the body not to metabolize it? So we see side by side, these look very similar, right? Let me see if I can. That's the difference I see. This right here, the OHs are gone. This is different, right? Other than that, the molecule looks very similar. So by changing those groups there, first of all, this is naturally occurring, right? Naturally occurring. This one is made in lab. So guess what? This is synthetic. You can patent it. If you make a recipe of something that did not exist before, you can patent this. It's synthetic, made in the lab. Splendor. Does it taste good? If you're not a super taster, yes, I'm not a super taster, so it's gonna taste good to me. It tastes sweet, and it has reduced calories because the body processes it differently. Okay, and for that reason, it doesn't really increase the caloric intake in your body when you're eating that. Okay, polysaccharides. On to compounds that saccharides. These contain 3 or more monosaccharides together. So branch polymer made up of repeating units of glucose, joined by a 1,2,4 beta glycosidic linkage. Here's the thing. Here's another low-calorie food, right? Celery. Cellulose is found in the cell walls of all plants where it gives support and rigidity to wood, plant stems, and grass. Humans do not possess the enzyme to hydrolyze cellulose. In chemistry, what we call hydrolyze in biology is digest. Okay, we're thinking chemical reaction, hydrolyze water to break up, right? In the world of biology, that would just be digest. Because we don't have the enzyme required to break apart cellulose fibers, we can't digest it. So they usually say, if you want a 0-calorie food or even a negative calorie food, eat celery. Don't eat it with too much peanut butter and then say it's a low calorie. Peanut butter cancels all that out, okay? I mean, the peanut butter itself, yeah, But we cannot digest celery, so it's usually considered a good fiber also because we can't really, break it down. Okay, so moving on here. Cellulose makes up insoluble fiber in our diet, which is important in adding bulk to waste to help eliminate it more easily from our body. So here is a structure of cellulose. You can see there your linkages right there. These are the ones we're going to be looking at. So we have a beta 1,4 linkage, yeah, right there, because you can see it's kind of diagonal. We're using this one here, so that's going to be beta. So what do you think about this question? Cellulose is water insoluble, right? Because water cannot digest it. So we're told here water can't break it down. Water cannot break it down into monosaccharides, despite its many OH groups. Based on the three-dimensional structure, why do you think this is so? Why do you think that cellulose cannot be broken down by water? That's a deep question, right? Because remember before we said that if something was water soluble, then for every one hydroxide you had so many carbons and all that stuff. That rule was for organic chemistry, and it applied there. Now that we're dealing with polymers, this is a whole different scenario. We're going to start dealing with biomolecules, right? The molecules get so big, sometimes the chemistry rules stop applying. So they're asking you here, you have a three-dimensional structure of cellulose. Overall, it looks linear to me. If you ask me, it looks kind of linear. And they're asking you, even though it has hydroxide groups, this is considered insoluble. So why is it insoluble even though it has hydroxide groups? Okay. So I'm trying to see, do they answer this later on? Okay, I don't think that they answered this later on. This reminds me of when we're talking about plaque early on and how the way the molecules are structured, it makes it easier for them to pack very close together. And so when I look at this right here, I'm going to let you think about it and completely answer it. I'm just giving you my hypotheses. But this reminds me, because it looks very linear, it reminds me of what happens with the insoluble fats we were talking about earlier, the ones that pack close together and form plaque in the body. This gives me that same behavior, where if your polymer is very linear, it can pack very tightly and it makes it very difficult. First, number one, we don't have the enzymes to break it down. Number two, water can't break it down. And so it makes it very complicated for this to be broken down in the human body. It does have a very valuable use though. It does create bulk, which is helpful, as it said, for stool removal. Anyway, let me move on to this right here. We're looking at starch. Starch is another polymer, a different kind of polymer, and we can process starch. Most people can process starch unless you have some kind of deformity, not deformity, genetic mutation of an enzyme. Most people can process starch, right? So starch is a polymer made up of repeating molecules of glucose joined by an alpha glycosidic linkage. So here we had a beta linkage that made the structure align differently. Now we have an alpha glycosidic linkage. Starch is present in corn, rice, wheat, potatoes, most carby food, right? The first main type of starch is amylose. So we're looking at amylose right here, the linear form of starch. This has an alpha glycosidic linkage. Once again, look at the glucose to the left and use that to judge the type of linkage we have right here, okay? Moving on. We have a second type of starch called amylopectin. With this one here, now we start seeing branching in the molecule. We have a linear form, but there are parts that branch off right here. So in the branching, you see that one of the starch molecules on top is essentially branching into the starch molecule on the bottom, and this is called amylopectin. So I'm trying to move over here real quick. Amylose is an unbranched polymer linked by a 1,2,4 alpha glycosidic linkage. Amylopectin has two types of linkages. We see this kind, the one we have in amylose, the 1,2,4 alpha, but we also see the regular amylose polymers cross-linking. And when they cross-link, they use the 1,2,6 alpha glycosidic linkage. So this is where we see the cross-linking right here. So it almost looks like you have the amylose in the bottom, amylose On the bottom and the top, you have the amylose right here. And then between the top and the bottom, you have a linking. So you can see the carbon 1 here links with this carbon 6. If you remember at 1, 2, 3, 4, 5, 6. Essentially, this is it right here. Both starch molecules can be digested by humans using the enzyme amylase. So we do have amylase, and we are able to digest starch. The digestion of starch usually starts in your mouth, and we're able to digest this. So that's common for most people. I think I knew a girl in school one time who had an issue with her enzymes, and so she had an issue digesting starch. That was a very weird issue with her. There were so many things she couldn't eat because of that issue, and it was tough on her. Imagine not being able to eat a lot of starchy foods that we can eat and take for granted, right? We even decide to have a diet where we leave out all these starches. She couldn't eat a lot of that, so she was always very, very, very skinny for that reason. Yeah, she's always very skinny for that reason. I think she had to take like special medications and stuff just to be able to eat that. After all these years, I saw her recently. She's still very skinny because there's a whole group of foods that she just can't eat because of that. So it's tough. Genetic disorders, very, very tough. Okay, so glycogen. Oh, Gabriella, yes, yeah, it's interesting, huh? Yeah, glycogen is a major form of polysaccharides, and essentially, when you eat a lot of starch or glucose, it is stored in your body as glycogen for future use. Okay, so glycogen is stored in mainly in your liver and in your muscle cells. When glucose is needed for energy, glucose units are hydrolyzed from the end. So glucose is one of those. Glucose is essentially stored as glycogen. Glucose stored as glycogen in your body. If you need glucose real quick, the glycogen gets converted to glucose and released in your body. Okay? And because glycogen is highly branched, there are many ends available for hydrolysis. So essentially, glycogen is very easily and very quickly broken down to glucose as you need it. If you're working out, this is happening a lot as your body is using up glycogen to form glucose. So you see how it's stored in your muscle cells. So there's such a thing as overworking out. I love to work out. And yesterday I got a chance. As y'all were working on your exam, I'm like, yay. In 3 weeks, I finally get a chance to go work out. And I got a chance to go work out, and that was great. But there is such a thing as overworking out. And overworking out happens when people work out too much. So I'm oversimplifying this, but they work out too much to where they say they start to eat their muscles, so to say. Your muscle cell has to release all the glucose stored. At some point, if you don't have enough carbs, you're not keeping up your caloric intake, your body now begins to break down protein for energy because you run out of glucose. Your body has to survive, and your body got goals, right? And so that's when someone is working out too much, they look very, very skinny versus looking bulky and looking fit. They look very skinny, not in a good way. Okay, so now we're moving on to blood type. Apparently, these monosaccharides tie into blood types. So we see here there are 4 main blood types, A, B, and O. Blood type is based on 3 or 4 monosaccharides attached to the membrane of the protein of the red blood cell. So in your red blood cell, you have the membrane, which is kind of the skin of the red blood cell, and there is a protein there. The protein has one of these sugars attached, not one of these, 3 or 4 of these monosaccharides. And based on the monosaccharides, you will either have blood type A, B, AB, or O. If I remember correctly from memory, which is not very good, my memory is not very good, blood type O is a universal donor, right? That's the one that can give to anybody. And then blood type AB is a universal recipient. So let's see. Each blood type has the monosaccharides below. So we're seeing this. So each blood type, whether A, B, AB, or O, each of them has the monosaccharides below. So it has this, this, and this. All 3. That's what I'm understanding. Okay. Type A contains a 4th monosaccharide. So one of the ways they test for your blood type is by seeing what monosaccharides are available. Type A will contain these 3 and a 4th monosaccharide. Type B contains an additional galactose unit. So type B will contain these three plus an extra galactose, D-galactose. Type AB has both type A and type B carbohydrates. So type AB will have 1, 2, 3, two of these and the extra one. Two of the galactose and the extra monosaccharide, this one here. Oh, they show it to you right here. You can see, right? So type A has this, type B has this extra one, and then type, oh, they didn't show type AB. Really? They didn't show AB? AB should have both of these, right? AB should have both of these together. And then type O has neither. O is like doesn't have either. And so you can see here, right? Even though I don't have type AB drawn here, you can see why type O can be given to any one of these people. Type O can be given to this because it's missing stuff, so it won't interact with them. Type O can be given to this because once this person receives that, the fourth molecule is missing, so their blood will not react with this. Type AB can receive from this type O, type B, or type A because these molecules here are not foreign to type AB. On the other hand, for type O can only receive from type O because you see how type O's blood type is very simple? The sugars on their blood is very simple. It's missing all the additional stuff. So anytime they get any of the other blood types with all the additional stuff, we have problems, right? They have problems. So here you're told the blood of one individual may contain antibodies to another. Those with type O blood are called universal donors because people with any other type of blood have no antibodies to type O. Those with type AB blood are universal recipient because their blood contains no antibodies to A, B, or O. So there are no antibodies, to get to the biology side of things, from AB that will interact negatively against the blood they receive from A, B, or O. On the other hand, the people who have blood type O, they have antibodies that work against A, B, or AB. So they can't receive from anybody else but another blood type O. So, oh, that's the end. I feel like today's lecture was a little shorter, but yeah, that's the end of it. So this is where chemistry begins to interface biology, and yeah, biochem is a little different from the organic chemistry part. But this is all I have for today. Do you have any questions? If not, this is it. Okay, you're welcome. Have a nice evening.